In the last video, we discussed unit systems and how to express things with units and convert between units. So now I'd like to start to turn our attention toward actually thinking about how to describe the motion of something. So let's just imagine that you are taking a walk. So there you are. And let's say you're strolling along a nice leisurely pace. Something like that. So between each of these positions you occupy, 1 second elapsed. So I'll just draw a little clock and write 1 second. Oops, there's my little clock. 1 second. There we go. All right. So there you go, walking along the ground. Now let's compare that with somebody else who's walking along the ground. Oops, my bad. There we go. And we'll make them red, just make it a little more obvious. There we go. Maybe doing something like this. And again, we will put 1 second between each of these positions that the person occupied. Oops. All right. So just ask yourself intuitively here, pause and ponder if you need to, who's moving faster, the black person or the red person? Okay, and hopefully we agree that the red person is going faster, right? They're covering more ground in the same amount of time. Okay, so this gives us some idea for how we can start to talk about motion. We intuitively know that something's going faster if it covers more ground in the same time, so maybe we can leverage off of that. To simplify things out, we can create what are called motion diagrams. So in this case here, got a with our first person, we can draw them in just as some dots like this. And our other person, we could just draw as just some corresponding dots like that. We just draw a dot where the person was. And actually very carefully where we're drawing it is at their center of mass. This is the point about which they would balance in every possible direction. In a much more advanced course than this one, you eventually prove that for rigid objects, all motion of an object can be described as a translation of its center of mass. By translation, we mean just up, down, right, left, combined with a rotation about the center of mass. So if we don't care about rotations, so for now we don't care about rotations, if we don't care about rotations, then all we need to worry about is just where their center of mass was located. If we can say where their center of mass was located, we can say where their left eye or their right pinky or their left big toe is located, just based off of where their center of mass is located. So it turns out all we need to do to describe them is where their center of mass is located. And we could do that even, say, for something like, let's think about a rocket. In fact, how about you do this as a quick pause and ponder. I'd like you to think about what a motion diagram would look like for a rocket just after ignition and it's launching. Okay, so hopefully you came up with something like this. At t equals 0, it's sitting on the launch pad. And then with each successive time interval, it's covering up more ground. So maybe this is at t equals 5 seconds here or something like that. This would be a perfectly good motion diagram for a rocket that is launching. All right. So with that, we can start to think about how we can hang numbers on this. And with these motion diagrams, we could talk about their position by just imagining that you can somehow come up with some mile markers. Now here, maybe quite literally, you put a 0 mile marker here at the initial position, and then you count how many miles to the east the person is at each time. Or here, a natural choice would be to say that sea level is at 0 meters. And then you talk about how many meters above sea level the rocket is at any instant. Okay. Now, it turns out that to describe things, sometimes we can go with just a number, and sometimes we'll also need to have a direction with it. So this gives us two families of physical quantities, the ones that are vectors. So this is a number with a direction. Sorry about that. And it turns out that ones that we'll be encountering pretty quickly will be position, displacement. We'll define that in a minute. Velocity. And acceleration is coming down the road in a couple of videos. Okay, scalars are things that we can describe with just a number. So, for instance, temperature doesn't have a direction associated with it. Temperature, mass, it's just the number you read on the scale, time, and speed. So speed and velocity, even though they're synonyms in English, to a physicist there is a technical difference between them. Speed is just literally how fast you're going without regard for direction. Velocity is a speed with a direction. So 70 miles an hour is a speed, 70 miles an hour east is a velocity. So some of these might seem a little surprising, like why would you need why would you need a direction to describe a position? So let's go and take a look at that and see why we have to call this a vector, a number with a direction, which we'll find we can usually represent these with arrows. So if I'm trying to describe a position, let me just have an object that's in, we'll make it speed up a little bit, doesn't really matter. So this is t equals 0 seconds here, 1, 2, t equals 3 seconds here. So at t equals 0, we can say that the object is located at x equals 0 meters. Now, effectively what we have done is we have literally put a meter marker, if you will, right there. So this is just like it was the state line. Now, at t equals 3 seconds, we can say the object was located at x equals plus 5 meters. So if we just said it was 5 meters away, the thing is you could be east or west of the 0 meter marker. And here when we look at it, we say, oh wait, it's to the east of the 0 meter marker. So the arrow that we would draw for position, sorry about that, try that again. So the arrow we would draw for position is going to look something like this. And usually what we do is we write an X, and we stick a little funky half arrow thingy over it to indicate that's a vector. So it's a number with a position. So here, the number with a direction. So here the direction is entirely indicated by that plus sign, meaning that's to the right of the origin. So if we said -5 meters, that would refer to something that was off over here to the left 5 meters. So even though you can say, hey, it's just where you are on the number line, it's a recipe for how to get from the origin to where you are. So in this case, the instruction is, if we're saying that we're located at x equals 5 meters, that means start at the origin, move 5 meters right. That's the location I'm talking about. This isn't the only choice that we necessarily could have done. For instance, we could have decided that right here in pink, that this is x equals 0. So then this position here, if we think about it, to get from here to here, here to here, I would have to go left. And so in the pink coordinate system, this would be located x equals -1 meter. So this would be to the left of the origin. So this would correspond to my initial, this is my alternative 0 meter marker, is located right here. So then similarly, where was this initial position? Well, I'd have to go 6 meters to the left of the pink 0 meter marker. So in the pink origin, I'd be saying this location was x equals -6 meters by the same token. So conventionally, if something is to the right of the origin, we say that that's positive. Whoops. My bad there. So positive means, whoops, to the right of the origin. And negative means to the left of the origin. But that is not set in stone. That's the default assumption that physicists will make if you don't say otherwise. If for solving some particular problem, it makes sense for plus to be to the left and minus to be to the right, you are free to do that. It's just that you have to say that out loud and make that clear so that someone else looking at what you're doing would understand that that's the choice you're making now. But if you don't say the choice out loud, the default assumption is positive means positions to the right of the origin, negative means positions to the left of the origin. Now, we've already seen one of the weaknesses of position as something to describe motion. And that is that you are free to put the 0 meter marker wherever you want it. And so different people could potentially have different 0 meter markers. Now, this isn't the end of the world. It'd be very straightforward to convert between one person's measurements and another person's measurements. So it's not the end of the world if we have to deal with it. But when we're describing how things are moving in nature, one would hope that the laws of nature should not depend on us choosing where to put the 0 meter marker. And it turns out that a quantity that is more fundamental is something called the displacement. So this is the change in position. after some motion. So the symbol for displacement is delta x. Whenever you see a capital Greek delta like that, that's always read as change in. Then change in what? X means position. And whenever you have a change of something, it's always the final minus the initial. Now, physicists usually use subscripts to indicate when you have two different things of the same, two different instances of the same kind of quantity. So x means position, sub f, final. X means position, sub I, initial. So the physical dimension of displacement is a length, and typical units would be meters. So let's just take a look at, say, a car. So we got a car cruising down the road. Let's say the state line is located right here. And as we know, mile markers always start at 0 on the southern and western borders of a state. So let's say the car starts 2 kilometers west of a state line. Now, of course, the way they actually implement it would be some large number in the other state, but we could just as easily say -2, that means 2 kilometers west of the state line. So we'll go with that. So our car is initially located here. And, or sorry, at the end it's located there, my bad. So this is x final. And we had started driving east to west, 3 kilometers to the east of the state line. And yes, I know that my cars look like the Captain Crunch's hat, so just deal with it. Now, the displacement is just simply the straight line vector that takes you from the initial position to the final position. This may or may not be the final, this may or may not be the actual path taken. But to find our displacement, we can say, okay, the displacement is, okay, this is change in, change is always final minus initial. So this will be -2 kilometers. We got to keep the mathematical sign here, minus a +3 kilometers. So -2 minus 3 is -5. Oops, sorry about that. Is -5 kilometers. And again, we're going to interpret this minus sign here as meaning to the left. So what this means is at the end of the motion, our car ended up 5 kilometers left of where it started. Now, this does not necessarily have to correspond with the actual path the car took. For instance, the car could have taken some sort of crazy stuttery path like this and ended up there. And if you were to look at the distance on the odometer, that would be a lot bigger than 5 kilometers. Maybe it's 20 or something like that because of all the zigzagging. In fact, maybe it went so far as to overshoot the final position and come back. That's entirely possible too. So displacement is not actual distance traveled. It is just the shortest possible straight line path you can take from the initial position to the final. So in this case, 5 kilometers, negative sign means to the left. We ended up 5 meters left of where we started from without regard for the actual path for how we got there. It seems a little abstruse, but if you hang with it for another class or so, you'll see that this is a sensible choice. So just to get a bit of a start on that, we can go ahead and use this to define average velocity. So it'll take us another class to define the velocity, but we can at least start by defining an average velocity over some time interval. So, oops. There we go. Our average, so we would write this as V bar. Whenever you see a bar, this means, oh, I see the problem. There we go. My bad. Whenever you see a bar, this should be read as meaning an average value of the thing. Is defined. So when you see an equal sign that has a third line on it, to a physicist, this means by definition. So the average velocity is defined to be the displacement over the elapsed time it took to do the motion. So the displacement over the time. So this is displacement up here. This is our elapsed time down here. So since these are both change-ins, we can take this a little further and we can say the average velocity would be equal to x final minus x initial over t final minus t initial. Now, just a quick side note, this is usually 0, but it doesn't have to be. But most of the time we can rig things up so we choose the problem to start at t equals 0 just to make the math a little easier. So the dimension of this is going to be length over time because we're taking a length divided by time. And a typical unit might be meters per second. So to just flesh out one concrete example of that, let's say I've got an object moving to the right. Let me put down, so this is position. We'll say, let's work in feet. Why not? So we'll say this is 0, 20, 40, 60. In this particular case, we'll say that the person's moving fairly uniformly. So this is t equals 0 seconds. So this would be 1 second, 2 seconds, 3 seconds here. Let's say we are interested in the average velocity over the time interval from 1 to 3 seconds, just to make this concrete. Let's figure out what that would be. So the average velocity would be the displacement over the change in time. So x final minus x initial over t final minus t initial. So x final is going to be 60 feet. We'll be subtracting 20 feet. And we'll divide by 3 seconds minus 1 second because those are the times of day that the object was at those locations. So this would be 60 minus 20 is 40 feet. Over 3 minus 1 is 2 seconds. So this works out to be 20 feet per second. Now, since this is a vector, the sign means something. The plus sign here means that it was moving to the right. So if we draw in our average velocity vector, it's going to look something like this. We'll just say V average is 20 feet per second to the right. Now this will always point in the same direction as the displacement vector. Now here, just let me draw the displacement with a different kind of arrow just to make it a little more obvious I'm talking about something different. Here, delta x would be, well, 60 minus 20 is plus 40 feet. Notice I didn't draw these the same length. They don't need to be the same length. This is because the units don't match. This is feet per second, that's feet. You never do a meaningful comparison. I could draw my V bar to be longer, shorter, or the same length on the piece of paper as my displacement. Because the units don't match, I can't meaningfully compare length. However, they always have to point in the same direction. So I displaced 40 feet to the right, so I ended up 40 feet to the right of where I started from. This means that on average, my motion was to the right. So the velocity vector and the displacement vector better point in the same direction. All right, in the next series of videos, we will start to get a little more graphical with this and start to study uniform motion. So have a good one.